What's up, everybody? In this video, I'm going to be covering USACO's 2020 open contest at the silver level, problem number 1, social distancing. Farmer John is worried for the health of his cows after an outbreak of the highly contagious bovine disease, COVID-19. In order to limit transmission of the disease, Farmer John's N cows, where N is between 2 and 10 to the 5th, have decided to practice social distancing and spread themselves out across the farm. The farm is shaped like a 1D number line, so just like 1, 2, 3, that's the farm, with M mutually disjoint intervals, where M is between 1 and 10 to the 5th, in which there is grass for grazing. So mutually disjoint intervals, that's kind of a mouthful, but basically what they're saying here is if the farm is a number line, 5, 6, 7, 8, then there are patches of grass, M total patches of grass, that's the number of them. So if M is 2, that means 2 grass patches. And they're defined by disjointed, mutually disjoint intervals. That means that they will not have any overlaps, and they'll be separated from each other by at least 1 square. The cows want to locate themselves at distinct integer points, each covered in grass, so as to maximize the value of D, where D represents the distance between the closest pair of cows. Please help the cows determine the largest possible value of D. So what's going to happen is you're going to place cows. For example, we could put a cow here, a cow here, and a cow here. And in this case, D would be 2, because 2 is the distance between the 2 closest cows. If, on the other hand, I decided to try and place 1 more cow, I could place 1 there, 1 there. I could have 1 here and 1 here, but then D would be 1, because even though this is a distance of 2 and this is a distance of 2, these 2 cows in the middle are a distance of 1. And since they're a distance of 1, that means that that's D. That's my closest pair of cows. And the cows have to be placed on the grass. They can't be placed just arbitrarily. The first line of input contains N and M. N's the first value, M's the second. The next M lines each describe an interval. Let me slow down a little bit. The next M lines each describe an interval in terms of 2 integers A and B, where 0 is less than or equal to A, which is less than or equal to B, which is less than or equal to 10 to the 18th. 2 important pieces of information. One is that A and B might be equal to each other and also might be equal to 0. Second is these numbers are going up to 10 to the 18th. So you're going to need like a long integer for that. You probably won't be able to use a classic int. If you're not familiar with that, for C++ or Java, if you're used to doing like int x, you would just do long x. Python, you don't have to do anything different. Your integers already go up to infinity. No 2 intervals overlap or touch at their endpoints. A cow standing on the endpoint of an interval counts as standing on grass. That's another important piece of information. So what that's saying is if I've got a grassy patch from like here to here, if this is like 1 and 2 or whatever, I can have a cow standing at 1 and that counts as being on grass. The points are included. It doesn't have to be like at 1.01 or anything like that. Output format is the largest possible value of D, such that all pairs of cows are D units apart. A solution with D greater than 0 is guaranteed to exist. D greater than 0 is guaranteed to exist just means that the amount of open grassy patches is at least as much as how many cows there are. Cows won't be placed on half intervals. They're going to be placed on integer points. And the distance is always going to be measuring between the integer points, but we're not going to have a situation where we can't place all the cows. So let's write out the sample case here. I've got from 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. We have grass from 0 to 2. We have grass from 4 to 7. And we have grass just at 9 exclusively. And we have a total of, so that's 3 patches, 1, 2, 3. And then we have 5 cows to place. So if we wanted to place these 5 cows, just kind of eyeballing it, I would say, let's put 1 here, let's put 1 here, probably here's good, here, and here. All right, so then let's see what our D is. 0 to 2 is a distance of 2, from 2 to 5 is a distance of 3, from 5 to 7 is a distance of 2, and from 7 to 9 is a distance of 2. Let me make this a little more clear, by the way, that grass went all the way back to 4. So that would be one potential solution. Another potential solution is I could move this cow to the left and put that cow over here, in which case these intervals would shift. And then I would have, this would also be 2, and then this would be 3. Another potential solution is I could shift this cow over to the 6, like that, and that would become 2, and that would become 3. But regardless of how I'm arranging these, notice I can't get a situation where all of my intervals are 3 or higher. So I'm going to have a minimum interval of at least 2, and that's the sample output. So If you haven't already, I would take a moment to run through with paper pencil, try out a couple different sample cases, maybe make up some of your own data, and think about how this cow placement system is going to work. Once you've done that, go ahead and we'll talk about the algorithm. Let's see here, I'm going to draw number line. Let's do 0, 1, 2, 3, 4, 5, 6. Okay, so if you've done the bronze problem, there's a bronze version that's kind of similar to this, then you probably are familiar with this particular caveat. But if not, there's a particular issue when trying to figure out how to place cows. So let's say, for example, like I have to place 4 cows on this span from 0 to 6. Well, we can just look at that and say like, okay, so this is 1, 2, 3, 4, fine. But how do we actually solve that from a programming standpoint? Because when you're looking at this interval here, your first instinct probably is going to be place on the endpoints because you're going to want to maximize distance. So you'll place here and then place here. You'll then go through and say, okay, well, I probably should place one in the middle. But then now we've got to place that 4th cow. And if I place the 4th cow in between any of the existing points, I've got a distance of 1. And the reason why is because we can't just do this as a binary problem. This, in fact, has to be divided evenly by thirds. So what we would have to do to get this even is we pull this one out, and then we go 1/3 of the way here to place the first one, and then 2/3 to place the second one in this particular gap. Now, from a solving standpoint, this is actually fairly difficult to do because what's going to happen is when you get a long enough number line and you've got multiple grass patches and you're trying to figure out, where to place them. Like, for example, if I go back to this example case where I had, let's see, this was 0 to 2, and then 4 to 7, and then just at 9 only. I'm going to draw green here. So I had grass from 0 to 2, 4 to 7, and at 9 only. If we were to try and use this approach and place our 5 cows here, we might place one at 0, we might place one at 9. We're going to want to place the next one in the middle, which is probably going to be like 5. But then it's from here it gets a little murky. So that's the first problem, is figuring out how to deal with those intervals that have to be divided into thirds or fifths or any other prime number. Second issue you're going to run into is that when you're trying to figure out how to place these, your time complexity is going to be really bad. Because if you have a number line here, oops, that's not what I wanted to do. The pen. If you have your number line here and you have to search through the intervals in order to decide where to place one cow, and then you have to search through the intervals again to decide to place the next cow, and then find the largest interval by searching through again and placing the next cow. If you have to search through these intervals every time you place a cow, then the number of searches you're going to have to do is n total searches, 1 for each cow. And the number of intervals you have to check is m. So you're going to have O of nm. Now, that's a problem because if you go back and look at your complexity here, m is 10 to the 5th and n is 10 to the 5th. So if I have O of n times m, if I have to go through m intervals n times, I'm going to be at 10 to the 10th. 10 to the 10th is going to run me over my time complexity. So what we need to do is we need to figure out how to reduce one of these numbers if we're going to have to do a search all the way through, or we have to try and figure out a way where we don't have to do as many searches. So if we look at placing the cows, we've got, let me go back to the original here. This is 0 to 2, 4 to 7, and then 9 alone. And then I'm going to put my grass again, 0 to 2, from 4 to 7, and then a patch at 9. So we already have decided that we're not going to be able to search through and decide where to place a cow and do that for each cow. So what we need is we need a way that we can go through the intervals one time and attempt to do some sort of a solution. Now, this is a particular thing, and this, I can't stress this enough. This is a particular style of solution that comes up a lot in these kinds of problems. And what it is if you've got a problem where you're supposed to try and find some evaluation of whether or not it passes a certain condition, or to identify a certain number where anything larger wouldn't pass and anything smaller would pass, but you're trying to find a maximum. If you're trying to maximize your solution and you don't know exactly what that number is, there are going to be problems where it's actually easier, rather than trying to run the simulation and solve the problem, where you're better off trying to just guess at the answer and then verifying whether or not that answer is possible. So what that essentially is meaning is, if I am trying to find D and I don't know what D is, then I have two ways to find this. The first way is to run through the simulation and attempt to solve the problem. And then after solving the problem, go through and measure what D ended up being. But that solution is going to be the O to the M problem. The second approach is to make a guess at what D might be. For example, I might say, well, what if D is 3? And then try to place my 5 cows. So if D was 3, I would place my first cow at 0. And then I can't place it at 2 yet, so my second cow would go to 4. And then I can go 5, 6, 7, but then I can't place it 9 because that's too close. If D was 3, I would only be able to place 3 cows. That was a linear pass, but I verified that D3 is too large because I was not able to place all of the cows. So that means that D has to be smaller. So what if, for example, I tried a D equals 1? D equals 1. So I would be able to put my first cow here. My second cow could go on 1. Third cow could go on 2. Fourth could go on 4. Fifth could go on 5, and I'm done. But I have extra grass left over here that didn't get used. So what that tells me is that D of 1 works, but there might be a higher D that could work. So I'm establishing this baseline. D of 3 is too large. D of 1 works, but there might be a bigger number. So let's try D of 2. If I were to do D equals 2, D equals 2, then my first cow goes on 0. My second cow is going to go on 2. My next cow is going to go on 4. My next cow is going to go on 6. Next cow can't go on 7, so that's going to be the next cow on 9. D equals 2 works. So 1 worked and also 2 worked, but 3 did not. And that tells me that D equals 2 is the solution. So in order to try and make this efficient, what you're going to do is you're going to try and find a range of what is the maximum and minimum possible D. Now, the initial maximum minimums don't actually really matter that much. What you could do is you could say that D equals 1 would be your minimum, and maybe D equals whatever the total distance is from here to here would be your maximum. So in this case, 9. So we know that a distance between somewhere between 1 and 9 will be the solution. And if we only had 2 cows, then that would be the solution. I'd put 1 here and 1 here and we'd be done. But it depends on how many cows we have to place. What we'll do then is we'll pick D values, and then we'll see how many cows we are able to place. And if it's equal to our target, which remember in this sample case, we have 5 cows that we're trying to place here. And if we're able to place our 5 cows, then we know we have a solution. So I've got D equals 1, let's say 1 to 9, like that. So D equals 1 to 9. What I'm going to do is I'm going to binary search on this, with this being a min and this being a max. So if I'm going to binary search on this, my first D value that I'm going to attempt is going to be 5. If I'm doing 5, I would place the first one at 0. Next one's going to have to go to this interval at 5. Next one won't get placed. 5 is obviously way too large. So then now 5 becomes my new max. And then I've got a distance between 1 and 5. So I'm going to try maybe 3. And we already did 3 and 1 and 2. But you're binary searching on D. Now, the reason why this works is because we can verify whether or not a D is going to work with a linear pass through M. So that is M operations, essentially. We would have our list of intervals. We would place our first cow on our very first spot. And then whatever D is, we can add that much and see, is that more than this? If that's not more than this, then we can place the next one and go find the next spot. If it is more than that, then you have to move to the next interval, but you still have to be aware of this 0. So I'd say, okay, well, I'm at 4 to 7. I can place 5. That would be where the next cow goes, with a D of 5. If I had a D of 3, then I would, excuse me, go 0 to 2. I would realize that I can't place it on the range of 0 to 2. So I would have to continue, and I would place it on the 4. So there's a little bit of bookkeeping here, but essentially now what's happening is the number of guesses you have on D is essentially the length of your number line, which we saw was, what was it? 10 to the 18th. At worst, you've got a number line of 10 to the 18th. So you've got 10 to the 18th possible numbers to check. And we have M intervals that we need to check. But on this pass, the amount of D values you're going to have is represented by the log of 10 to the 18th. Because if you have 0 and 10 to the 0, if you had 1 as your minimum and 10 to the 18th as your maximum, and every single time you do a pass, which takes essentially about M steps, every time you do a pass, you're cutting this number in half. 10 to the 18th, what is log base 2 of 10 to the 18th? 59. Okay, so even though 10 to the 18th seemed like a large number, we've only got 59. So now I've got basically about 59 times M instead of N times M. 59 obviously is much smaller than N because N was 10 to the 5th. 59 is not anywhere close to that. So that's essentially what the approach is going to have to be. We get our pairs of numbers 0, 2, 4, 7, and we can't make a matrix or a number line that's a size of 10 to the 18th. It's going to have to stay as pairs. 9 to 9. We have our minimum value, a minimum D of 1, a maximum D will be whatever the last number is here minus the first number here, which is 9. So then our D values that we're going to try are going to be binary searching on these. So once we get a D value that we want to try, for example, 5, we start here. First cow goes at this number, and that's cow 1. You can keep track of it as you go, which means the next D is going to have to be 0 plus 5 because we're going from 5. So that's going to take us out of this range and put this into this range. We'll update our location to 5, which means our next one's going to have to be at 5 plus 5, which would be 10. We'll go to this interval. We get to the very end. If we didn't place enough cows, in which case we only placed 2 cows, first cow went here, second cow went here, then what we're going to have to do is we're going to have to roll back to the beginning, update our min and max with our new max now being 5, try a new D, in this case D could be 2, and then once again running through. So 0, that would be my first cow. That would mean my next position would have to be 0 plus 2, which is equal to 2. I would be able to place a cow here, which means that my next position would have to be 2 plus 2, which is equal to 4. I'd have to go to the next interval. I can see that there's a 4 here. So next one's going to have to be 4 plus 2, which is equal to 6. I can place that on the same interval here, which means next one's going to have to be 6 plus 2, which is equal to 8. I don't have anything in interval 8, so my next interval's at 9. I would have 9 there, and that would have been my 5 cows. Once I get my 5 cows placed, I want to update my min. If I successfully do it, that updates my min to whatever that D value is. And I'm going to keep working my way in until eventually min and max meet each other, just the same way as a binary search happens. Once that's happened, I'll have ideally some number that worked. In this case, 2 will have worked, and some number that didn't. In this case, 3 will not have worked, which would mean that 2 would be the answer. Alrighty, good luck coding it, and I'll talk to you in the next video.